In this project, my overarching objective was to build a reliable loan default classifier that performs strongly on the computation dataset while remaining well-fitted and stable under cross-validation. Rather than focusing on a single model or a single split of the data, I built a full end-to-end pipeline that includes feature engineering, model comparison, hyperparameter tuning, cross-validation, threshold optimization, and multiple diagnostic visualizations to access model fit. I began with data pre-processing and feature engineering. Instead of relying solely on the original variables, I construct additionally business-driven features designed to better represent financial stress and browser risk. For example, I create a loan-to-income ratio to measure repayment burden relative to the earning. I also engineered an interest burden variable that captures how much actual interest payment pricing to browser experience relative to income. In addition, I create a credit age ratio that normalizes the credit history legends by the applicant ages, which helps distinguish between a younger browser with a short but healthy history with an older browser with limited credit pace. I also introduced a composite risk score combining known present income and interest rate, capturing both exposure and pricing risk simulation. This engineering the features improved prediction quality because they encode non-linear financial relationships that raw variables are also may not fully express. Next, I compared three different models: logistic regression, random forest, and light GBM. Logistic regression, random forest, and GBM Logistic regression provides interpretability and simplicity with struggles with non-linear interactions in financial risk data. Random forest captures non-linear and interactions effectively, but can be less computation. Uh, After light GBM as a gigantic boosting framework combines strong practice power with efficiency and scalability. After evaluating their performance on a validation split, tree-based in-place methods clear outperformed the linear model, and Light GBM provided the best balance between practice strength and scalability. Based on this comparison, I selected GBM for further optimization. To address a class imbalance on the dataset, I use the class datasets typically contain fewer defaults than non-defaults. And ignoring imbalance can bias the model towards predicting the majority class by assigning balance class weights. The model pins misclassification on the majority class more heavily, which improves sensitivity to default risk without distorting the original data distribution. In addition, I later applied decision thread tuning to further optimize classification behavior from a business perspective. For hyperparameter tuning, I implemented randomized search CV over key light GBM parameters, including the number of estimators, learning rates, tree dips, number of leaves, and sub-semining ratio. Random search is competitively efficient and allows exploration of a broad hyperparameter space without exhaustive grid search. After tuning, the optimized configuration demonstrate meaningful improvement compared to the based model. indicating that the model capacity and reorganization balance had been better aligned with the data size structure. To exercise model stability and avoid overfitting to a single split, I implemented a stratified five-fold cross validation. This approach improves that each fold perspective the original class proportion, producing more reliable and stable performance estimates. Instead of reporting results from one split course validation agree with performance across multiple folds, while reducing variance and increasing confidence in the model's generalizability. This validation strategy directly addresses the rapid requirement to access and improve model fit using key-fold validation. I also examined learning curve to understand whether the model was overfitting or underfitting. This training performance remains high across increasing sample size, while validation performance improves steadily as more data is introduced. Although there is a moderate gap between training and validation curves, the validation curve continues to rise rather than plateau early, stressing that the model benefits from additional data and is not severely overfitting. This indicates that with larger data size, predict performance could likely improve further. The confusion matrix provides insight into classification trade-off. In a loan approval context, false positive correspondence to approving applicants who ultimately default, with which results in financial losses. False negativity repeat learning, leading to opportunity cost. The optimized model deferrals and minimize incorrect approvals. From a business standpoint, managing false positive models structures allows adjustment on the balance in through tuning. The Prussian recall curve further extruded performance under class balance because default events are less frequent. Prussian recall analysis is more informative than ROC curves in this setting. The curve demonstrates that the classifier maintains high precision even as recall increases, indicating strong separation between risky and safe process. This confirms that the model is not simply predicting the majority class but meaningfully distinguish the default risk. Instead of using the default probability cutoff 0.5, I perform the threshold optimizing by evaluating a range of possible decision thresholds and selecting the one that maximizes the overall classification equality. This step is importantly because the default threshold is arbitrary and may not align with business risk tolerance. By adjusting the threshold, the institution can tighten approval standards to reduce default risk and loosen them to increase loan value. This flexibility adds practical value beyond raw predictive performance. If I had more time and resource, I would integrate external data sources such as Microsoft Micro Indicator, regional unemployment trends, and broader credit behavior features. Economic circle strongly influence default probability, and income macro level variables could improve robustness across time. I would also implement practical monitoring strategies dedication to ensure that the model inputs meaning remain constant over time. Or finally, I would experiment time with ensemble staking or probability calibration to further refine predictability. stability. In summary, I built a full modeling pipeline that incorporates feature engineering, multimodal comparison, class imbalance handling, hyperparameter tuning, stratified cross validation, learning curve diagnostics, confusion matrix analysis, operation recall evaluation, and threshold optimization. This approach ensures that the classifier is not only strong in predict performance, but also well fitted, stable, and aligned with business decision-making requirements.